All right, good morning, chemistry students. How are you guys? We have, trying to think here, one or two more lessons on kinetics, and then we are done with our first completely online unit. So take a minute to look at this do now, give it a shot. There are 3 questions. Again, as a reminder, guys, this is your review. So, definitely pause the video and try to answer these questions. All right, I'll pause it too. All right, before we get started, I was like, you know what? Everyone else is doing all these online lessons like in their pajamas, so I think I would do it too. I'm in my little hoodie here. But no, Barone's still wearing a tie. All right, we keep it professional here. Here we go. Back to work. Now, for our lesson for today, the do now, it is about naturally occurring isotopes of sulfur. So let me switch on here. The 4 naturally occurring isotopes of sulfur are S32, S33, S34, and S36. The table below shows the atomic mass and the percent natural abundance for these isotopes. All right, immediately you should be thinking about that lab we did with the little marbles and the different sized spheres that you guys weighed. We did a lab like this with percent abundance. We did questions where we solve for the average, the numerical setup for the average atomic mass, and they're going to ask you to do that in number 52. So let's break this down. Number 51. State both the number of protons and the number of neutrons in an S33 atom. Well, you don't even need to use the table for that. Like I said, I'm a big push for me is when you guys see these questions, a lot of times they come in clusters. So don't assume that you can't answer any of them just because it looks really scary. Dig into each question. And can you get one of the 3 right? Can you get 2 of the 3 right? Go for it, right? So this is number 51 is, I think, a pretty manageable question. So the number of protons, that always deals with the symbol of the element. So S has, oh, that's not right, chemistry reference table. S has, let's see, right here, S has 16 protons. That number, the atomic number, tells you the number of protons. So S has number of protons, write it down, 16 protons. Now, how do you figure out the number of neutrons? How many neutrons does this have? Well, it's the mass minus the number of protons, and in this case, that should be 17. So you should have 16 protons and 17 neutrons. And there would be a space provided in your answer booklet for you to write that, but if you get the answer, you're good. Number 52, in the space in your answer booklet, which we don't have, we're going to do it off to the side, show a numerical setup for calculating the atomic mass of sulfur. All right, this is where it gets a little tricky. This is going to be tough for me to write it down here. But the rule is you take the mass and you're going to multiply it by the percent abundance as a decimal. There's a couple of ways to do this. Some of you guys who are really good at math, you could also just multiply this times this all the way across, add them up, and then divide by 100. But the way we learned it in class was the following. We moved the decimal point 2 to the left. So that becomes 0.9499. These ones here, they get tricky. You move the decimal point 2 to the left, and you actually get 0.0075. In this case, you would get 2 decimal points to the left. You would have 0.0425, and this one, move the decimal point 2 to the left, you would have 0.0001. So what you're going to do is you're going to multiply each of these numbers by the percent abundance as a decimal, and you'd get some value. And after you get that value, you would add them all up, okay? So 31.972 times 0.9499, you get a number. 32.971 times 0.0075, you're going to get a number. 33.968 times 0.0425, and then 35.967 times 0.0001. And then you get all those individual numbers and add them up. And guess what, guys? You should get a number that's pretty darn close to this, 32.065. Your answer should be essentially that. But it's important that this question does ask you guys to show the numerical setup. So just writing the answer would not get you the 1 point here. You actually have to show the numerical setup, all right? For the sake of time, I'm not gonna be able to do that, but that's how you do it. Number 53, compare the energy of an electron in the third shell of a sulfur atom to the energy of an electron in the first shell of the same atom. It's a memory-based type question. As you get farther away from the nucleus, those electron shells have more and more energy, okay? So essentially, an electron in the third shell would have more energy than an electron in the first shell. That's just a sort of something that you have to remember. All right, so those are your do now questions, and we're gonna move on. Our objective today is to read and text code a Regents question and summarize it in their own words, verbally and in writing. That's the sort of language objective. The actual content that you need to know is you're going to explain what a catalyst does to a reaction. We talked about a catalyst earlier in the collision theory lesson, but we really didn't talk into too much detail as to what it does. We're going to talk a little bit more about that today, and then we'll answer some Regents questions, and then we're going to move on. Here's your meme of the day. I had a colleague who said I should have switched the two young ladies and made that your sleeping all day is over here and your online learning is over here. But hey, hopefully you guys are staying. The goal is to resist the urge to do a lot of sleeping and social media and Netflix and all that, and to really stay on top of what you're supposed to be doing at home with your online learning. So I know it's kind of a joke. It's kind of funny. Remember, it's important to stay up to date with your online learning in all of your classes. All right, here we go. Turn and talk. Reminder, this is a review turn and talk. What are the different ways to speed up a reaction according to collision theory? So sure, go ahead, turn and talk to your partners, people who are in your house with you. I'll try to cover up the answer choices down there. What are the different ways that we learned that you could speed up a reaction? Why don't you guys pause the video and think about it and look at your notes. All right, so welcome back. So there's a number of ways to make a reaction happen faster. The most common way, and like I said, this is a pretty common question on the Regents too, and the one that students go to most often is, hey, increase the temperature. The particles start moving faster, they collide more often, and increasing the temperature is the easiest way to increase a reaction's speed. Other ways you could have said, if they're in the gas phase, you can increase the pressure. You could also decrease the volume. You could make the reaction container smaller, which forces them closer together. So we have increased temperature, increased pressure, decrease the volume. And then we get into some of the other ways. You could increase the surface area. That's like by stirring something or crushing it up into smaller pieces. That exposes more of the surface of the reactants to each other. So increasing the surface area and stirring also are ways to speed up a reaction. And then sort of the point of today's lesson is you could add a catalyst. Okay, so we're gonna see some of those right now. Did I forget any? Oh, concentration too. We could have increased concentration as well. So if you make them move faster, they collide more. If you give them less space, they collide more. If you squish them closer together with pressure, they collide more. If you add more stuff, they collide more. If you crush it up into smaller pieces, you have more surface area for collisions to occur. These all increase the number of overall collisions. And if you increase the number of overall collisions, you in fact get more effective collisions. That's what collision theory says. A catalyst is a little different. It doesn't increase the overall number of collisions. It increases specifically the number of effective collisions so that when they do collide, they collide in the right orientation. And we're going to talk about what that means. All right, so there's this sort of mini paragraph here about a catalyst, and I'll read it to you guys. You can copy it down if you'd like. A catalyst is a substance, which is an element or a compound, that speeds up a chemical reaction by taking a different reaction pathway that lowers the activation energy. It does not change the final products of the reaction. So a catalyst participates in the reaction, but it doesn't change the final product. So you still have the same, let me do it this way, you have the same reactants and then the same products, okay? But you have something in the middle that the catalyst allows the reaction to take a different pathway that has lower energy to get to the final products. And we'll talk about what that means. All right, so take a minute, look at this diagram. You see that you have the diagram that we've been looking at now for the better part of a week. You have with a catalyst and without a catalyst. So take a minute, pause the video, think about what's happening here and see if you can use potential energy and activation energy in your answer. So maybe describe to me what you think is happening. Pause the video, think about it. All right, so welcome back. You guys should be able to see here that you have without a catalyst and with a catalyst. The one thing that's important to note is that they both have, in terms of potential energy, the potential energy of the reactants and the products do not change. Okay, so the first thing you want to know is a catalyst does not change the potential energy of the reactants or the products. Okay, however, the activation energy, that is not necessarily the case. So for without a catalyst, I'll do that in blue, the activation energy of the forward reaction goes from there to there. So that's my activation energy of the forward reaction. And here's my activation energy for the reverse reaction. Without a catalyst, you have that as your activation energy. Now, so this will be 180 minus 40. The quantity here is going to be 140 kilojoules. Okay. So 140 kilojoules, whereas over here we have 180 to 120. That's going to be 60 kilojoules. Okay, so you can see what your activation energies are without a catalyst. When you add a catalyst, you get a sort of a different value for each of the activation energies. So for this one, the activation energy of the forward reaction now with a catalyst, it only goes to here. So you can see that you've actually lowered the activation energy. Okay, and the same thing goes for this one. Here's my activation energy of the reverse reaction with a catalyst. Okay, so now we've sort of reduced it from 140 to 100. So it's only 100 kilojoules now required to get the forward reaction started, and you only need 20 kilojoules here for the reverse reaction. Okay, so it does cause a change. So the first part of that definition, going back here, is that it lowers the activation energy. Well, if you ever forget, you can kind of use the graphs to help you out. The potential energies of the products and reactants are not changed, but the activation energies are. And then the other thing that I always sort of imagined when I was a student like you guys is it takes a different path. It's a different line, and I always remembered it as like a sort of different path from start to finish. We start and end at the same place, but it takes a different path. And so that's how I always remembered it. Okay, so what we're gonna do is we're gonna practice a little bit of that. You can see here's the path without a catalyst, and it's got a different path than the path with a catalyst. And it does so by lowering the activation energy. All right, so I've actually shown you guys that here, okay? All right, so this is like another version. I did all the doodling on the previous slide, but you see here, there's the activation energy of the forward reaction without a catalyst. And you can see that here's the activation energy with a catalyst, and that you're actually you're reducing the activation energy by 40 kilojoules. All right, so let's get into, you see the same thing here, okay, the same effect. Let's get into some questions now. You guys get the premise, but now let's talk about how the Regents exam could ask you questions about this. So why don't you take a minute, pause the video, read the question, and think about it. Okay, so hopefully you had time to think about it. Like I said, when it comes to a catalyst, I can literally think of like maybe 2 or 3 ways that they ask you questions. And if I don't get to all of them by the end of these, I have a handful of example questions. I'll sort of go over them verbally. But in number 19 from some old Regents exam, it says a catalyst increases the rate of a chemical reaction by blank. So immediately, again, using our strategies from in class, try to sort of like, I always try to like ignore the answer choices. And I think about what the answer would be to me. What would I fill in this blank with? And then I go see down here if it matches. So what I do is I go back to move myself here. I go back to that definition, and it speeds up a reaction by taking a different pathway and lowering the activation energy. So we're thinking about 2 things, a different pathway with a lower activation energy. So go back to the question. A catalyst increases the rate of a chemical reaction by, I'm looking for something that A, deals with a different pathway, or B, deals with lowering the activation energy. So let's see what we have. Providing an alternate reaction pathway. That certainly sounds like a different pathway. So that's good. Let's make sure all the other ones then don't make sense. Providing the required heat of reaction being delta H. In that definition I gave you, is delta H referred to at all? No. So we're definitely not going to be looking at number 2. Increasing the potential energy of the products. Again, we're not talking about potential energy, we're talking about activation energy. And in fact, going back to our slide here, we found out that the potential energies of the reactants and products stay the same. Okay, those red arrows are the same both with and without a catalyst. So potential energy of reactants and potential energy of products are not changed. We are dealing with activation energy. So this question says we're increasing the potential energy. That's not true. The potential energy is staying the same when you have a catalyst. Okay, and then the activation energy. All right, increasing the activation energy of the reaction. So now we have these 2 answer choices that suddenly seem like they're plausible because they both include the component that was in the definition, the reaction pathway and the activation energy. So now that we got rid of 2 and 3, let's pause the video. Hopefully you got down to 1 and 4 too. Pause the video again and tell me which one you think it is and why. All right, so hopefully you had some time to think about it. Certainly providing a reaction pathway sounds reasonable, but the activation energy does too because it's in the definition. But what's the problem with number 4? We are not increasing activation energy, we're actually decreasing the activation energy. So it's not number 4, your answer is number 1. And for a little bit of visual proof, again, go back to that slide that we doodled on here. Without a catalyst, we have 140 kilojoules as our activation energy for the forward reaction. When we add a catalyst, it decreases that activation energy. It does not increase it. It lowers the activation energy. It does not raise or increase the activation energy. So that one's incorrect. Number 4 is incorrect. Number 1 is right. All right, let's look at another Regents question. Pause the video, think about it, look at your notes, see what you come up with. All right, so what occurs when a catalyst is added to a chemical reaction? Again, you should be thinking about, oh, it's asking about catalyst. We're talking about a different reaction pathway and lowering the activation energy. So let's see which answer choice most reflects that. An alternate reaction pathway with a lower activation energy. Again, that sounds pretty darn good. An alternate reaction pathway with a higher activation energy. Remember, the catalyst lowers the activation energy, so we're going to steer clear from number 2. Number 3, the same reaction pathway. Right there, we know it's not the same. With a catalyst and then without a catalyst, it has a different path, 2 separate lines. They have a different reaction pathway, so number 3 is out. Number 4, the same reaction pathway. Again, we're going to steer clear from that because it's not the same pathway. It's a different reaction pathway. We don't even need to read the rest of it, and then even that is wrong. A higher activation energy is incorrect. So the answer is number 1. It's just asking you to use your definition of catalyst to get a question right. All right, I think I have 1 or 2 more here. Number 12. I like this question. It adds a different little wrinkle to it. So pause the video, answer this question, and then we'll go over it and do our exit slip. All right, welcome back. So this is a cool question. It sort of asks you guys to make a few different connections here. Which intervals, well, it says given the potential energy diagram for a reaction, so they give you this potential energy diagram, which intervals are affected by the addition of a catalyst? All right, so this is good. This is a very good question. What gets changed when you add a catalyst? So take a minute and, again, think about that. So there's a couple of ways to tackle this. The way I would do it is, first of all, I would sketch what would happen if you added a catalyst. According to all the pictures we saw, you would start at the same place, but you would take that, quote, different pathway. And then you would end at the same place. So you would draw a line like that. So in blue here might be what you would expect to see if you added a catalyst. Well, look, let me switch colors here. Arrow 2 would be the same no matter what because you're starting and ending at the same place. This is the potential energy of the reactants. So number 2 is not changing. Number 4 represents, ask yourself, what does 4 represent? 4 represents the delta H. Okay, that is your delta H here. And that also is not going to change because you're starting here, starting and ending at the same place. So arrow number 4 doesn't change either. So arrow 4 is not going to change. So 2 doesn't change. 4 doesn't change. So we can get rid of those. And you're already down to only one answer, which is number 2, which is arrows 1 and 3. And I will do that we'll do purple. So here, this is without a catalyst. And if you were to add a catalyst, arrow 1 would change now to something like this. Okay, you can see that now it's only going to go to the top of this arrow. So arrow 1 would change, and then arrow 3 would change. Instead of going from the x-axis to the very top of the peak, now it doesn't need to go as high because the activated complex is not as high. So arrow 3, which we don't talk about as much, that's the potential energy for the activated complex. So arrow number 3 would change as well. So it's arrows 1 and 3 would be the ones that change. Okay. All right. So that was a tough question. One thing before we go over the objective, and then I show you guys, get you guys set up for the exit slip. There is one other question, and this I want to end with this one because this here, this blank diagram with all the labeled arrows will oftentimes make an appearance on the Regents exam. And I wanted to show you guys a couple of other alternate ways they could ask you questions. So if you could imagine for a minute that all you have is this blank diagram, the question might say, what value is represented by arrow number 1? And you'd need to say that's the activation energy of the forward reaction. What value is represented by number 4? And that's the delta H. You know, they might ask you to identify the names of these arrows. That's super common. I've seen this in part 2. If you were to get rid of these arrows and you just have this blank diagram, they'll say sketch the way the potential energy diagram would look like if you added a catalyst. And they'll actually ask you to sketch a line like this in your answer booklet, where you show starting at the same place, the potential energy of the reactants is the same, and then you have the alternate pathway that has a lower hump, and then it goes and ends at the same place. So they'll actually ask you to sketch a line in your answer booklet to show what would happen if you added a catalyst. So those are other questions that sometimes appear. All right, our objective was to read in text code a Regents question and summarize it in your own words, verbally and in writing. I think we did that. And then now I hope you can explain what a catalyst does, and it is going to reduce the activation energy, as well as provide an alternate pathway for a reaction to occur. All right, guys, that's it. That is your lesson on catalysts and interpreting PE diagrams. Your exit slip will be posted in a bit. See you guys.